Hello everyone, I am Mohammad Ahmad Qureshi, working as an assistant professor in Civil Engineering Department at RNG Patel Institute of Technology, Bardoli. Today, we will study design of reinforced concrete structure subject and in which we will study earthquake resistant design of building. We will just see the basics of earthquake resistant building in this lecture. So, first of all, we know that earthquake forces are random and unpredictable in nature. So, the calculation procedure of earthquake forces is described by IS code 1893 2002. So, in this IS code, all the procedures related to earthquake forces are described in detail. So, we will just go for seismic methods of analysis. Once the structure model has been selected, it is possible to perform analysis to determine the seismically induced forces in the structure. There are different methods of analysis which provide different degrees of accuracy. So, the analysis process classified on the basis of three factors. First, the external action means whether it is static analysis or dynamic analysis. Then, the behavior of the structure. Second is your structural behavior. The behavior of the structure or structural materials can be further classified into nonlinear static analysis or nonlinear dynamic analysis. Means your structure should be elastic or should be elastic plastic. So we can perform the analysis by using the structural behavior. And the third classification is according to type of model. So whether it is 1D, 2D or 3D, it depends on type of model. So different methods of analysis provide different degrees of accuracy. Hence, the analysis process is classified by these three factors: external action, whether they are static analysis or dynamic analysis, and structural behavior, whether it is elastic analysis or elastic plastic analysis, and last is type of model, that is 1D, 2D, and 3D. So, these are the analysis process. Now we go for methods of elastic analysis. Generally, for regular structures with limited height, seismic coefficient method, or the other name for seismic coefficient method is static coefficient method or equivalent lateral force method. This method is used for structures with limited height. And these all methods are covered in elastic analysis in IS 1893 Part 1 2002. So first of all, your first method is seismic coefficient method, and the second method is response spectrum method, and the last one is elastic time history method. All these methods for elastic analysis are covered in IS 1893 Part 1 2002. Generally, your seismic coefficient method is used for regular structure with limited height, and the response spectrum method and elastic time history method are under the category of linear dynamic analysis. The significant difference between linear static and linear dynamic analysis, that is the effect of external action. The difference between linear static and linear dynamic analysis is nothing but it is the level of force and their distribution along the height of the structure. In external action, generally two types of analysis are there. First is your static and second is dynamic. So the significant difference between both the analysis is nothing but the force level or level of the force, and their distribution means force distribution along the height of the structure. So in this chapter we will study seismic coefficient method. As I discussed earlier, we know that earthquake forces are random, and hence it is unpredictable in nature. Earthquake forces are unpredictable. So the entire calculation procedure of earthquake forces is described in IS 1893 Part 1 2002. And as per this IS code 1893 Part 1 2002, we have to assume that the earthquake forces are static in nature. We have to assume that the earthquake forces are static in nature. What do you mean by static? Static means it does not change with time. And we know that if we consider only static condition, then what will happen? The forces will not vary with time. And we know that the seismic forces are lateral forces. Suppose this is your building. So On this building, the seismic forces may be in this direction, it will act maybe in this direction, it will act maybe in this direction. So, the seismic forces or the earthquake forces are lateral forces. So, lateral forces normally acts from any orthogonal directions. Hence, we have to study such type of forces in this chapter. So, first of all, your first step is determination of base shear. What do you mean by base shear? Base shear is nothing but total expected seismic forces at the base of building along principal direction. Hence, the total design lateral force or design seismic base shear along any principal direction shall be determined by the equation VB equals to capital AH into capital W. This equation is given in IS 1893 Part 1 2002 page number 24 clause 7.5.3, where what is your VB? Your VB is nothing but base shear, or you may also say that it is total design lateral force at the base of the structure. And second is your AH. AH is design horizontal acceleration value. And your last is capital W. That is nothing but seismic weight of building. So, by this way, you may calculate the base shear. We will see in next PPT regarding the calculation of AH and W. So, first is your seismic weight. What do you mean by seismic weight? It is nothing but self weight of all structural components of building. This is called seismic weight. Seismic weight of the building is sum of seismic weight of all the floors. Means in building, whole building, you will easily get the weight of all floors individually. So generally, the seismic weight at any floor level is equals to the dead weight of the floor system plus the appropriate amount of imposed load. Generally, the seismic weight of particular floor is calculated as dead weight of slab plus weight of beams plus half the weight of columns above and below the floor plus half the weight of walls above and below the floor. So, in seismic weight, we have to include one more parameter, that is imposed load, live load. As per IS 1893 Part 1 2002, Clause 7.3.1, the percentage of imposed load is to be considered in seismic weight calculation. So, this table is given in IS 1893. And one most important thing, remember this, for calculating the design seismic force, for calculating the seismic design force of any structure, the imposed load on the roof need not to be considered. Remember this line. For calculating the seismic design forces for any type of the structure, the imposed load on the roof shall not be considered. And the percentage of imposed load should be 25 for loads up to and including 3 kilonewton per meter square, and for live load above than 3 kilonewton per meter square, the percentage of imposed load should be increased up to 50%. These both parameters will come under examples while solving the numericals related to seismic forces. Just remember this word, on the roof need not to be considered. Now next, design horizontal seismic coefficient AH, where we have seen AH in the determination of base shear in the equation VB equals to AH into W. So your horizontal acceleration AH would be determined by IS 1893 Part 1 2002, page number 14, clause 6.4.2. Here you have the equation, that is AH equals to Z by 2 I by R SA by G. So from this equation you have to calculate the horizontal seismic coefficient AH. For any structure, remember one thing, for any structure with time less or equals to 0.1 second, the value of AH will not be taken less than Z by 2, whatever be the value of I by R. Here, the unknown Z is zone factor. Z is your zone factor. Your I is importance factor. and R is response reduction factor. And your last component SA by G is average response acceleration coefficient. We will study all these parameters. Now, first of all, we will go for Z, that is zone factor. Zone factor, that is Z, it depends on the city of India. The Indian map is divided into number of zones as per earthquake prone severity of area. So the zone depends upon the seismic zone, that is zone. Z factor depends on the seismic zone, and as per IS 1893 part 1 2002, for the seismic intensity low, the zone is given name as second. For third zone, the seismic intensity is called moderate. For fourth zone, the seismic level is severe. And for fifth zone is very severe for seismic intensity. And the zone factor, that is Z value, for second zone is 0.10, for zone 3 it is 0.16, for zone 4 it is 0.24, and 0.36 for zone 5. So zone factor value are given in table in your IS code 1893, and for the maximum considered earthquake, the values for different zone are given in this code. Next, importance factor. Importance factor generally depends upon the functional use of structure. Characterized by hazardous consequence of its failure, or post-earthquake functional needs, or historical value, or economic importance. So, the value for importance factor is given in IS code 1893, clause 6.4.2, clause 6.4.2, and depends upon the type of structure, the value of important factor changes as 1.5 and 1. For the important service and community buildings such as hospitals, schools, monumental structure, emergency buildings, railway station, fire station building, radio stations, and large community halls like cinemas, assembly halls, subway stations, or power stations, consider the value of importance factor as 1.5, and for second, that is all other buildings including your residential buildings, the value of importance factor is 1. So in the examples you will be given that what type of building it is. So according to the building, you have to take or consider the value of importance factor. Next is your response reduction factor. So what is response reduction factor? Generally, R depends on the expected seismic damage of the structure. It is the factor by which the actual base shear force that would be generated if the structure were to remain elastic during earthquake shaking. It is called response reduction factor. Simply, it depends on the seismic damage performance of the structure, whether it will be your ductile deformation or your brittle deformation. So, response reduction factor for different building systems are given in clause 6.4.2. For building frame system, that is OMRF, ordinary RC moment resisting frame or special moment resisting frame, the values of R would be 3 and 5 respectively. For steel frame with concrete concentric braces or eccentric braces, the value will be 4 and 5 respectively. For SMRF frame designed as per SP66 buildings with shear wall, the value of response reduction factor should be 5. And for load bearing masonry buildings, whether it is unreinforced, reinforced, or reinforced with vertical bars at corners, its value will be 1.5 and 2.5. And for ordinary reinforced concrete shear wall, the value is 3. And for ductile shear wall or building with dual system, the value should be 4. Generally, the ordinary shear wall with OMRF and ordinary shear wall with SMRF are given in 4.15.2 clause number, and ductile shear wall with OMRF and ductile shear wall with SMRF are those which are designed and detailed as per IS 13920, and mostly these values are prohibited in zone 4 and zone 5. Next parameter is SA by G. Simple, your average response acceleration coefficient, that is SA by G, it depends on time period and the type of the soil encountered. So, it is the factor which represents the acceleration response of the structure under earthquake ground vibration. It generally depends on your time period and your type of the soil. So, here in figure, your SA by G values for 5% damping of the structures is given. For other damping values, remember this thing, for other damping values of the structure, multiplying factors given in clause 6.4.2 shall be used. So, generally this figure is for 5% damping only. And for other damping values, you have to multiply the factor which is given in clause 6.4.2. So, how would you check your SA by G value depending upon the time? So, suppose here you got the value of time, or we can say that the natural period zero point 0.5. So, you have to just draw a line like this, and depending upon the type of soil, that whether it is rock soil or hard soil, medium soil or soft soil, you have to just connect your SA by G coefficient like this way, and from that you will achieve the value of SA by G as 2. This is just for an example. Suppose you have time period zero point 0.5, then you will get for rock soil the SA by G value as 2. By this way, you have to calculate the value of SA by G for different periods of time. Lastly, the fundamental natural period, that is TA. The fundamental natural period TA for the buildings are given in IS 1893 Part 1 2002 Clause 7.6.1, and they are classified as TA equals to 0.075 into H raised to 0.75. This equation can be used for moment resisting frame building without brick infill panels, RC frame. And the second equation is given as TA equals to, that is fundamental natural period, equals to 0.085 into H raised to 0.75. This equation is for moment resisting frame building without brick infill panels for steel frame. And lastly, TA equals to 0.09 into H upon root D. This equation can be used for all other buildings, including moment resisting frame with brick infill panels. Remember this equation, TA equals to 0.09 into H upon root D, where your H will be the height of the building and your D will be base dimension of the building at the plinth level in meter. Suppose this is your building, so this will be your height of the building and this will be your D, that is base dimension of the building, along the considered direction of the lateral force. Remember this thing. Now, our next will be distribution of base shear. Generally, the base shear calculated above, that is VB equals to AH into W, is to be distributed along the height of the building. As we had seen earlier, that the significant difference between the linear static and linear dynamic analysis is the level of force and their distribution along the height of the structure. So, the base shear, that is VB, that we had calculated in the first step, is to be distributed along the height of the building. So, the shear force at any level depends on the mass of that level. Remember this thing. The shear force at any level depends on the mass of that particular level and the deformed shape of the structure. The earthquake studies of the building indicates that the top portion of the building suffer more damage than which one? Than the lower one. Thus, this top story and this is your lower one. So, these top stories should be subjected to larger force. Hence, VB shall be distributed along the height of the building as per the equation Q equals to VB into WI HI square upon summation of I equals to 1 to n, whatever the number of floors, Wi into Hi square. This equation is given in IS 1893 part 1 2002 page 24 clause 7.7.1, where your Q is nothing but lateral force, your Wi is nothing but your seismic weight of particular floor. Suppose this is your first floor, then here will be seismic weight of floor 1, seismic weight of floor 2 accordingly, and here Hi will be the height of floor measured from the base. Remember this thing. This height of floor will be measured from the base, and your n is your number of storage. Your n will be number of storage. So for regular building, suppose we assume that this is your first floor, second floor, third floor, fourth floor, fifth, and your top floor, that is sixth. So according to the floor, your weight will be differ. Hence, you have to distribute this force base here according to this figure, as we had seen that the top storage should be subjected to larger forces. Hence, and the shears will be distributed by like this. Hence, by this way, we can determine the seismic forces and shears at each floor level using seismic coefficient method. So, we will just go through whole method quickly. So, first of all, your seismic method of analysis. There are three different methods of analysis, and all the methods of analysis which provide different degrees of accuracies. So, based on the type of external action and behavior of the structure, the analysis can be further classified as linear static analysis, dynamic linear analysis, non-linear static analysis, and non-linear dynamic analysis. And the significant difference between the linear static and linear dynamic analysis is nothing but the force level and the distribution along the height of the structure. Generally, the seismic coefficient method is used for regular structure with limited height, and in linear dynamic analysis, seismic spectrum response spectrum method and elastic time history method are generally classified. And we know that the earthquake forces are random and unpredictable in nature. Hence, the calculation procedure of earthquake forces is described by IS code 1893-2002. And remember one thing, we have to assume that the earthquake forces are static in nature, and hence, we consider only static condition, means the forces are not vary with time, and the seismic forces are lateral forces which acts from any orthogonal directions. So your first step will be determination of base shear. You may calculate the base shear by using equation VB equals to AH into W. Then you have to calculate the total seismic weight of the building. Then you have to calculate the imposed load. But in imposed load, remember one thing, that the live load on the roof need not to be considered. Then design horizontal seismic coefficient, that is AH equals to ZI SA by G into 2R, and zone factor will be determined according to the different seismic intensity. Then the importance factor for the different types of building will be calculated. Then the response reduction factor, which generally depends on the seismic damage of the structure, should be taken from clause 6.4.2. Average response acceleration coefficient depends on the time period and the type of soil, and this figure is generally for 5% damping. And if your damping is other than 5%, then you have to multiply the factors which are given in clause 6.4.2. And fundamental natural period, three different values for RC frame, steel frame, and with brick infill panels. And lastly, you have to draw this figure and you have to distribute the lateral forces as well as shear from top to bottom of the building. Thank you.